Hi, this is Simon and this is Pieman Maths. This is a short video about number sense. So this is about understanding the value of numbers by using various different pictorial and concrete representations of them to enable you to better see the relationship between numbers, so therefore to become more fluid and more flexible in your use of numbers, and ultimately to become a better mathematician. Hope you enjoy. Making sense of numbers. So, what is number sense? I'm just going to answer that by saying what number sense isn't, or things that perhaps stopped us from being able to develop number sense in the past. Too often expectations were placed on learners to just get on with maths. And they would have to do this without knowing what numbers look like. So you're asking a child something that you think as a more accomplished user of maths that they can do as well. Come on, let's count in twos. Okay, I defy you to count in B's in the alphabet. That's hard. Think of that when you're trying to get a child to count in twos. So that would then kind of lead into not having an understanding of quantities and concepts like more or less. When you're counting in twos, you are literally adding 2 each time. And as a result of all of this, children would lack the understanding to enable them to be more flexible in the use of numbers, and therefore to become more confident and to be able to count in twos, to use that example again. So learners can develop their number sense with a range of representations of numbers to help them to see the value of numbers and to better understand mathematical concepts like the one about more or less. So here we are now getting into the nitty-gritty. This is looking at representations. Here we have 5 and we have 4. Now individually they're digits, but they are numbers as well. But what do they mean? What does 5 mean? What does 4 mean? What is the value of 5 and the value of 4? Not sure? Need a picture. Here we go. Here's a picture of 5. That's what 5 looks like. That's one we've all seen before. That's the classic die or dominoes arrangement of 5, and very similarly 4 looks like that, just without the extra one in the middle. So you can start thinking there about concepts like more or less by comparing just these two. This is how powerful a picture is. Even better than a picture is a concrete representation. Here are some tomatoes I picked from the garden the other day. Or you could use plastic toys, plastic dinosaurs in this case. And then of course we have a name for them. We call them 5 and we call them 4. Okay, so those are the representations. That's what I mean by a representation. How does this feed into the various curriculum? Well, in the English curriculum, the Welsh one I presume is probably very similar. We have things like in year 1, read and write numbers from 1 to 20. Year 2, that extends to reading and writing numbers from 1 to 100. In years 1, 2, 3 and 4, there is a curriculum requirement to identify and represent numbers. And then in years 2, 3, 4, 5 and 6, we've got things like comparing and ordering numbers. So a picture to understand what these things are worth is invaluable. And now we come on to starting to understand more or less. So adding and subtracting 1 and 2. Here you can see on the left hand side there are 5 beads on the number line. If we add 1, we get 6. So there's a picture. You can see 1 added to it, and there's 6 in total now. And there underneath you can see the number sentence which goes with it. 5 plus 1 equals 6. Now you can go backwards and take that 1 away again. So in reverse, you now have 6 minus 1, 6 take away 1, 6 subtract 1 equals 5. And then let's just go back again to 6 again. So you've got again 5 plus 1 equals 6. So there's that relationship between adding and subtracting, and in this case just 1 at the moment, but we can extend it to 2s and then of course to any other number. How does this feed into the curriculum? Well, for year 1, we have adding and subtracting 1 and 2 digit numbers up to 20. In year 1 also, we have identify one more and one less from a given number. And then in year 2, we start adding and subtracting a 2-digit number in ones and even a 2-digit number in tens. And year 3, adding and subtracting 3-digit numbers in ones, 3-digit numbers in tens, and 3-digit numbers in hundreds. These ideas are all helpful in all of those curriculum requirements. Now, benchmarks are incredibly useful as well. Now, our number system with our base 10 that we use with our 2 hands, that's where it comes from. That's where the word digital comes from digit, your fingers. Okay, so 5 and 10 are natural. They're the natural benchmarks. Here's a number of green discs. Now, if you count them, you find that there are 7, but that's quite difficult to count them like that. That's where the benchmark idea comes in. Watch. As you can see now, we know it's 7 because you can see there's 5 red discs and there's 2 blue discs. That's what makes it easy to see it as 7. Much easier than when it's arranged along the top of the screen. Difficult to supersize 7, especially when they're arranged like that. But arranged like this, you can just see those straight away. And with practice, learners can see it straight away as well. And also, there's 3 gaps there, 3 spaces missing, which then indicates that you can see that you need 3 more from 7 to make 10. And here we are now with our number bonds to 10. These are the pairs of numbers that add up to make 10. And here, again, using the idea of the benchmarking, we have the tens frame with 5 red and 5 blue discs. So the first statement you can make, you can do it in any order, but I'm doing it from 10 all the way through to 0. Here's 10 plus 0 equals 10. Or because we haven't taken any away, we say 10 minus 0. It still leaves us with 10. 9 plus 1 equals 10. Or 10 minus 1 equals 9. These are the pairs, aren't they? 9 plus 1 is the pair of numbers. So the bonds to 10 are 9 plus 1 in this instance. Here's 8 plus 2. 7 plus 3. 6 plus 4. And here we are at the halfway point. 5 plus 5 equals 10. Double 5 equals 10. Or 10 minus 5 equals 5. 10 subtract 5 equals 5. 10, if you insist, take away 5 equals 5. 4 plus 6 equals 10. 3 plus 7 equals 10. 2 plus 8 equals 10. 1 plus 9 equals 10. And here we go. 0 with 10 added gives you 10. So this feeds into the national curriculum with representing and using number bonds and related subtraction facts within 20. This is for year 1. And then for year 2, this is showing that addition can be done in any order. This is commutativity, but subtraction cannot. If you noticed, we would have had 7 plus 3 equals 10, or 3 plus 7 equals 10, but you have to be careful when you're subtracting 7 or 3 away from 10. You have to do that in the correct order. They can't be switched. And of course, we have bonds for other numbers. Here are bonds up to 8. And the commutativity idea is highlighted here. 8 is 5 plus 3, or it's 3 plus 5. Again, doesn't matter. Commutativity can be done in any order. This is for addition only. Subtraction is a different story. Okay, and again, this is in year 2, showing addition can be done in any order, but subtraction cannot. So there's 8 minus 0, still leaves us with 8, and so on. So we've established that number bonds are fantastic things to use when you're doing maths. Okay, but when is the best time to use them, or how is it best to use them? Here's an example. If we think about this question, 7 plus 8, we're going to ideally kind of know number bonds for 7 and for 8, and also 10 will come into the equation as well, won't it? Right, so I think we'll split up 8 such that we can have a chunk that goes together with 7 to make 10, and then add the rest on. 8 is made up of 3 added together to 5. Okay, why have I chosen 3 plus 5? Well, here's why. 7 plus 3 equals 10. So I've used the 3 out of the 8, so now I've just got this 5 here left to add to the 10 here. Adding something to 10 is a really easy thing to do. Children need to be told and shown how easy it is, but it is a really easy thing to do. So 5 plus 10 equals 15. So there's our answer. 7 plus 8 equals 15. Now again, this comes into the Year 1 curriculum with represent and use number bonds and related subtraction facts within 20. Of course, this is exactly that, isn't it? 7 plus 8 gives you a number, 15, which is within 20. And again, I could have split up the 8, or rather split up the 7 into 2 and 5 and got the same answer. So for Year 2, show addition can be done in any order. That's commutativity, but subtraction cannot. Okay, so that was a relatively nice example, a simple example, working with single digit numbers. You can do it with any number you choose to do when the numbers are in the right arrangement. Okay, so take this example here, 499 plus 367. The temptation might be to think, oh, I can do this. I know an algorithm I can use for this. I can do 499 and I can add it to 367 in a nice column. Now that would work, okay, but that's quite long-winded. Look at 499. 499 here is very, very nearly 500. What do you need to add to 499 to get to 500? Well, it's 1, isn't it? So split the 367. 367 equals 1 plus, obviously it's 366, because you've spent time now and you know that the number that comes immediately before 367 is 366. So now the 1 here added with the 499 here gives us 500. So 500 plus what we've got left here, 366, gives us 866. It's a nice example there of using number bonds to do something mentally. This is a Year 3 issue. Add and subtract numbers mentally, including a 3-digit number and some ones. And also going into Year 5, add and subtract mentally with increasingly large numbers. You're getting well on the way now to being able to do lots and lots of things. So this idea about number bonds and adding ones becomes even more powerful when you consider you can do this with decimals as well. Have a look at this one. 5.99 plus 0.23. Now, we've got things that come into play here like place value, and it gets a bit more complicated, but the basic idea is that 5.99 added to 0.01 gives us 6. 6.00. Let's make it with 2 decimal places just to match everything else that's on this question. But where's that 0.1 come from? Where does this come from? Well, it comes here from 0.23. 0.23, and you've taken off 0.01 gives us 0.22. And this can be added to 6.00, which gives us the answer of, this is all done in your head, 6.22. You see how powerful it is? And this is a year 5 problem, or this is a year 5 curriculum level, solving problems involving numbers up to 3 decimal places. And finally, and perhaps you knew this was going to come along, you can actually apply this to fractions as well. Here's an example of a fractions question. So 6.5 added to 2 3/4. What can you split up to make this more easy to do? Well, I've written this question such that you can see that 6.5, the idea is to try and get up to a whole number. So what do you add to 6.5 to get to a whole number? Well, if you add a half, you get 7. Okay, but where's this half come from? Well, it's got to have come from here, from 2 3/4. Well, 2 3/4 is actually 2 1/4 plus this half that we've used. So we've used the half, which is there, look. So we've got 2 1/4 to add to our 7, which gives us our answer of 9 1/4. There you go. That's how powerful number bonds are. And this is a year 5 question, adding and subtracting fractions with different denominators and mixed numbers using the concept of equivalent fractions. That's not to go into the depth of that one there, but we know that quarters and halves are in a related family. So 3/4 includes a half and another quarter, which was the number bond that we were able to use to help us work this one out. There we are. There's some ideas for you to help your children with number sense. If you remember, we started off with the idea of having pictures and representations, concrete representations, to actually show you the value of numbers. So we had, if you remember, we had the tomatoes and we had the plastic dinosaurs to stand for 4 and for 5. And we also had the picture of the dominoes or the dice. That's very powerful. We then moved on to being able to add 1s and 2s to a number, or to take off 1 or 2 from a number. And then we did a look at number bonds, so number bonds to 10, number bonds for other numbers as well. And then we did some calculation right at the end. So we had some, from a relatively simple example, we used this idea about number bonds, and we were able to apply that to some relatively complex, certainly from year 5 and above, work with fractions at the end there. Hope you enjoyed it. Stay tuned for the next video.